it was already yesterday. The hyperspectral was mentioned several times today also. So I think it's starting to be a known technology, but it's still good to kind of go through the different possibilities where it could be used and how it could be used. On the preliminary discussions presentation yesterday, there was a discussion about how the photonics could help to produce more biomaterial. So that's one of the things I would definitely like to go through today. How we can more thoroughly use the biomaterial, how we can get everything out of that, how do we know what we are using, how we are using. So that's also one of the things I want to discuss today. So Juha mentioned in the morning that there's quite a lot of optics companies in Finland who are actually quite old. So Specim has been around for quite a long time, 23 years. We are originally also a spin-off from the VTT, and we are fully located in Oulu at the moment. We have more than 60 people working in the company, and the turnover at the moment is about 12.5 million euros. And I would say last year was extremely high growth for our company. It's the growth of the whole technology. It's not just our company, but we definitely have set reasonably high targets for our growth for the future. We manufacture push-broom technology. I'm not going to go into the technical details, how our cameras work and things like that today. I want a little bit more concentrate on the application themselves. But push-broom, a line scanner system, we are really capable of putting that from the lab to the industry, on the field measurements, on the airborne measurements. And we are really supplying quite a large variety of the products. So we have optical components, we have the cameras, we have the full measurement systems from the airborne to the field. And we really cover a really broad wavelength range from 400 nanometers to 12 micrometers. So really from the visible range up to thermal ranges. And which wavelengths can be used is really dependent on the application itself. It's still good to give a couple of slides about hyperspectral itself. So it's really a combination of digital imaging with the spectroscopy. So the idea is to really image a target, collect a full spectrum, reflection, emission spectrum, or whatever, how the application works for every pixel. And all the materials, they have specific spectral signatures. So if you think about the forestry vegetation, this is now just covering from 400 nanometers to 2500 nanometers. So you can see what you have. You have the chlorophyll, you have the red edge. People are talking already about the multispectral cameras dedicated for the red edge detection. That's the measurement what you are. You have the water absorption, you can go to proteins, you can go to lignin, cellulose. So what's the difference between the multispectral and the hyperspectral? With the hyperspectral, you are really collecting the full spectrum, continuous spectrum. You are able to analyze lots of different things, lots of different details from the one measurements, while the multispectral cameras are collecting just few wavelengths, dedicating on a certain application. And since all the materials, all the different kind of phenomena, they have different kind of spectral signatures. You are really able to kind of locate materials. For example, this is a certain type of forest species, look from the airborne measurements, or you are able to look on the chemical and physical properties. There's, for example, above ground carbon content, which is measured, analyzed directly from the airborne measurements. Even though the technology has been there for quite a while, it's not thoroughly used in the forestry. There are technical limitations, there has been price, there has been performance limitations, but on the title of the presentation I put that, okay, we are talking from the seedlings all the way to the end products. So I have few slides about the different levels where you could actually apply this kind of technology. If you think about the forestry, if you think about the circular economy, if you think about the bioeconomy. So first of all, the phenotyping. These pictures are actually from our customers, who are working on this kind of automated greenhouse. So the idea on the phenotyping is that you are really producing a lot of, in the case of forestry, seedlings. You are really growing a lot of different kind of genotypes of plants. You are treating them in a different way. You are giving more water to them. You are giving a little bit of different amounts of light for them. And how you are able to kind of track them is that the robotic system is really taking the plant one by one. Okay, there's lots of weighting, there's a measurement of the heights and things like that. But then you have a cabinet where these plants are measured separately with the hyperspectral camera. And by doing this, different plants have been treated in a different way. You are able to understand how different genotypes, how different types of plants are actually behaving on different kind of environments, the different kind of environmental changes. Are they resist for the water draft? Are they resist for high water? Are they resist for cold temperatures and so on? So you are able to speed up the breeding process by selecting the most suitable plants for different growing conditions. So I would say that this is one of the possibilities which should be used also in the forestry. And there are applications, there are cases, we have customers who are already doing it not necessarily with this kind of automated way, but it would be a possibility. Okay, it's I have learned from the biologists that it's good to measure the plants in the laboratory, inside on the artificial conditions. But what is more important in many cases is to understand how the plants are actually behaving in the real conditions. And hyperspectral, it has been complicated, difficult. Couple of years back, if you look at this image, it's not about forestry, they are measuring mushrooms, but if you think about that kind of condition, it was not possible to take the hyperspectral imaging onto that kind of field condition. Now we have the full hyperspectral imaging system with the data processing and everything in this kind of small box. So you are really able to put this on the backpack, you are really able to go to the forest, you are really able to screen, survey, finding the issues. So that if you are really going around seeing that there's a certain kind of trees, certain kind of plants that have the issue, now you have the possibility to make the point measurements, understand, make the model, build the understanding with this kind of technology, and really make the measurements of the plants, if it's trees, crops or whatever, but you are really able to take this technology into the areas where your actual plants are growing. Of course, we started in the company, we started from the airborne measurements. And that's still one of the biggest things where our technology is used. So I have split this into a few different levels. So of course, large scale airborne surveys are one of the biggest areas for the hyperspectral still. It can be about environmental studies, it can be about forestry, it can be about the agriculture. But in practice, these are done with the large planes. The idea is to make the surveys of the really large areas, kind of small ecosystems. And we really are providing the high-end hyperspectral instrumentation for these ones. So it's normally a big plane with a big instrumentation covering a broad wavelength range. There's lots of information collected. Tree type identification, biomass, forest resource planning, forest fire kind of identification, problem identification, of course inventory, invasive species detection. So you are really able to cover a large area. Coming from yesterday's talk, multispectral works in certain ways. If you are only selecting a few wavelengths, you are able to detect, for example, in Finland, leaf trees from spruce and pine automatically, no problem. If you want to separate different kind of leaf trees from each other, then you have to go deeper into the hyperspectral. But definitely the technology is available for really large-scale surveys. A new thing which we have been, I was actually talking here in 2015, then I was giving a couple of slides about this technology. But still in the large scale measurements from the planes, sun-induced fluorescence. So one type of special hyperspectral instrumentation, we are really able to go directly into the photosynthesis of the plants. So the idea is that global chains, carbon cycle, all these are important. So with this kind of measurements, where we are measuring how much the photosynthesis fluorescence is coming from the plants, we are measuring directly that one. We are able to understand how well the plants are actually taking the carbon dioxide. We are able to also understand what is the vegetation health level, what is their stress level, and so on. And in Specim, we developed this technology for Research Center Jülich in Germany. We started from the field measurements. We took that to the airplane level, which you can see here. And now the European Space Agency is taking that to the FLEX satellite. We are not building the technology, but in the same method. And on 22 forward, there will be a satellite tool to really monitor the carbon cycle with the large ecosystems. If we come down from the large scale measurements, or we come to the kind of field level, then of course we have the possibility of making our devices smaller. You can see one of our cameras on a UAV on a Hydra model there. We have customers putting these on the field level, integrating them on the machines. So really measuring small areas, repeating measurements, the same kind of things, stress, I would say diseases, different kind of issues with the vegetation, how much fertilizers they need, and so on. But I would say that when we come down from the large scale measurements, there's normally time for the processing. When we go to the UAVs, when we go to the field level, the results must be available as soon as possible. So when it goes to smaller scale, it goes to smaller to the end users, and we have to focus on how to get the results there. From field to the end product, I would say that technology has been getting faster. This was already on the table like 15, 20 years ago, that they want to measure the quality, for example, of the wood, parquet, and these things like these. At the moment, it's back on the track because we have been able to build and develop more faster devices. You are able to match the color, you are able to make the quality of the final product going to the end users good. You are able to detect automatically detect different kind of remains of glue, what kind of water content you have on the bark, do you have resin, do you have knots, and so on. So I would say even in the mechanical processing, if you are barking the tree, how much bark, how much sap you have left after your processing, that's possible to detect with the hyperspectral imaging. Biofuel, a little bit touching the previous presentation. Of course, moisture would be really nice to have. Hyperspectral is a surface measurement. We cannot go into the material like we can do with the radars. But for example, optimizing the burning process. So if you have in-bed furnace, you are burning wood, you are burning turf, you have a mixture of these. But with the hyperspectral imaging, you are directly online able to measure what material goes into the process. You are able to slow down the process, and you are able to get the more optimized measurements from there. And of course, quality, getting the kind of foreign object, how much soil you have, how much water you have, and so on. So you are really able to optimize that a lot. And of course, the circular economy, recycling. We want to make sure that we are using everything from the wood. So this is a picture from the Zen Robotics. So really sorting out the bio-based material from to be used as a biofuel. Most of the waste is construction waste. Wood, so they are building new buildings, they are tearing down buildings, they are repairing buildings, they are generating lots of wood. How to automatically take that away, take the wood away from that part so the hyperspectral. But of course, we need the sensor fusion. Zen Robotics, they have 3D, they have hyperspectral, they have normal cameras. So it's not just a hyperspectral, but you really have to be able to control lots of things. And I just want to end with this one. This is our new kind of strategy, spectral imaging made easy. So that's how we see the future. We want to change this technology. We have made it faster, we have made it smaller, but we just want to make it so that the customers are able to quickly access it with the easy data processing, fast data processing, and use it in the different kind of application fields. So thank you.
Thank you very much, Jussi.
Kari Nieminen from InnoCAD Oy, and I have 4 short questions. First of all, the camera on the table, what is the weight of that camera?
1.3 kilos.
1.3?
Yep.
And the price?
List price for one unit is 15,000 at the moment.
Okay. And are you offering also the software that with which you can process the data?
Yes.
Okay. If you have chance to buy either such a camera or infrared camera, is there any sense to buy an infrared camera?
It depends on your application. So unfortunately, this is now limited to between 400 and 1000 nanometer. So it really depends what kind of material you are working, what is your application, what you want to find from there. So normally I would say for the vegetation, this is really good tool. You can get really a lot of information out of that. If your problems are requiring longer wavelengths, then you have to think about the infrared camera on the side.
Okay, thank you.
So how deep to the surface it goes? How deep surface it measures?
It really depends on the material. So we are really mainly, most of the cases we are looking at the scattering of the light, reflections of the light. So if it's a really porous material, you can go down to, let's say, 0.5 millimeter, a couple of millimeter. But normally I would say it's really in the surface, few hundred micrometers on the surface where it gets the results.
Okay, I can continue from that question then. Regarding the ecosystems, and especially if you are also from Oulu, X-rays are not included to photonics, right? But in some cases, because you can't go with these wavelengths to the deeper to see the, for example, the foreign objects in recycling, and when we are talking about now this circular bioeconomy, the EU strategy is now public, by the way, and the circularity seems to be one of the key messages there. So how about combining different kind of equipments in for example, recycling? Does it make it more efficient, or is it just big cost?
I would say that it's a must. It has to be done. So that, for example, the robotic system, what the Zen Robotics making, they really need the 3D to understand what is the size of the material. Then they have the normal high-speed camera to get the really texture of that one, hyperspectral to get the information about the materials. But we have customers who are already now using the hyperspectral together with the X-ray, so that they are really combining these. So I would say that the sensor fusion is one of the main things where this kind of photonics communities should actually work. So we have to get the understanding who are the partners, who are the working. If we find an end customer with the problem, we have to be able to kind of see that, okay, we know the companies in Finland, we know how to focus, we know who can solve radars, we know who can solve the X-ray, who can solve the hyperspectral, and then the processing on top of that.